There's a bunch of
Because when I did
So we finished chapter 1, and today we skip up the chapter 2 just for the time being, and we go to the chapter 3, the orbital maneuvers, and then once we finish these chapters, then we go back to chapter 2. The orbital maneuvers is this. The concept is this. For each orbit, its energy is we know is mu divided by 2a, and a is the 2a is is the major axis, and or 0 or positive, I would say. So this is for elliptic orbits. This is for parabolic orbit, hyperbolic orbits. And so as long as your mechanical energy determined, then basically that object is kind of docking onto the specific orbit. So that means once you, the mechanical energy, we on the other side we know is v squared divided by 2 minus mu over a over r. So for example, here we consider this is the Earth, and this is a certain launching site. So once at the launching site, this is the radius, which means the Earth, and so we say the launching velocity is v. So basically, at this moment, at the very, very beginning, the launching speed has determined which orbit you're going to be docking, right? So that makes sense. And at this site, the r equal to radius of the r of the Earth, and v is simply determined by the initial speed, the launching speed there. So basically, that depends on how you determine your launching conditions. You have predetermined the orbit you're going to dock. Once you have that thing, everything been settled down there, unless the satellite itself has its own small engines. Most of the time, it has small engines for changing the orbit. Okay. So the concept is this: if we want to have this one, this object is to move to say the different orbit, then how can we do it? Okay, and that is the issues we're going to talk about in these chapters. And furthermore, the different topic is, say, if this is, if the object is on a circular orbit, I make another scenario. Okay, for example, if this is an International Space Station, and say if you cargo, the space shuttle taking the cargo and want to give a logistics supply to here, and somehow during the launch the cargo, this space shuttle is here. They are on the same orbit, okay, but they have a different phase angle or distance away from. To that moment, if you be the pilot of the space shuttle, how are you going to do about to deliver the cargo to here? Think about this. On Earth, we simply take the paddle, speed it up, right? If you're going to here, you take the paddle and speed it up, what happens? If you speed it up, basically you use the own thrust of the space shuttle. You're going to give the space shuttle a bit more velocity. That means you're going to bring the space shuttle to the different mechanical energy. That means you're going to bring the space shuttle to different orbits. Holy cow, you make the situation worse. Right? Okay. So that is a way, there's a special way we call the orbit facing. So that means we have to say this one would be go to the internal smaller orbits, and hopefully taking the small orbits, they have the shorter period of time, and hopefully when they say I want to move here, so when that moment happens to here, then both will already go here. And then to that moment, then you space out to the second thrust, and to reduce the speed. In this way, they can meet together at the same place at the same time. Okay, so that is the second topic we want to talk about in these chapters. And those kind of things, and we can utilize we can just utilize the techniques we learned in chapter 1. And we simply is to manipulate between the mechanical energies and the geometry, and we can do those things. Okay, and at least per se we can do the rough calculation. As far as in details, the kind of fine tuning, that one we won't be covering. And also, I'm not prepared for that one yet. Okay, so but at least we can talk about the general procedures for this one. And so this is a general introductions for what we're going to learn about these chapters. And the first one I want to talk about is the very simple Hohmann orbit transfer. Of orbits. Okay, for the Hohmann transfer, that is the thinking is this: assuming this is the initial orbit. This is center here, and for simplicity, with assuming this initial orbit is spherical, okay, but the concepts can be applied to the elliptical, and assume circular, and the target again, that is assume circular orbits. Okay, and then we also assume the two orbits, they have the same common center here. Okay, and now we simply want to see how, say, the satellites on the initial orbits can be transformed, can be transferred to the new orbits. And there's quite a few ways to do about that one. And many methods can do this one, and all the methods are determined depends on how much fuel you want to expend. The larger the more fuel you can expend, then you have more degree of freedom to do it. And Hohmann transfer is pretty much, in general speaking, is the most fuel efficient method. And the way doing is this. Here I describe the concept, and then we're going to do the detailed calculations. The way is this: assuming this satellite is circulating in counterclockwise directions. Once it comes to here, and then we take on the transfer orbit. The transfer orbit is going to bring this one to the target to the top here, and taking an elliptic orbit. This is called the transfer orbit. And definitely, this is elliptic. And this is the half cycle of an elliptic transfer orbit. And this transfer orbit basically is tangent to initial orbit at the South Pole here, tangent to the target orbit at the North Pole there. And that is the definition of we call the Hohmann transfer. Okay, and this most of the time is the most fuel efficient. I would say most of the time, and not always, depends on the relative size of the orbit. Okay. So now we, from here you can see the initial orbit, say we have this distance, let me call it R1. And the final orbit, we have some radius, we call it R2. So clearly, you can see the transfer orbits have the major axis R1 plus R2, right? And with all the information ready, then we can do something. We can determine, at this point, we need to have certain data V. So let me use color. Okay, that's the transfer orbit. So at this point, on the initial orbit, the velocity equal to that. So let me call this called the V1. At the same point, if we want to be changing to the transfer orbit, at the same point here, they must have a corresponding velocity. I don't know the magnitude yet. I just schematically drawing it a little bit larger. I don't know yet, but they shouldn't be different. So this is the velocity we call it on the transfer orbit. Okay, at this point. So let me say this point is say the transfer point. Let me call it transfer point 1. Okay, so that is the V1. Let me stick with my label, whatever. Okay, later I will going to change my symbol. So those are the velocities on the initial orbit and on the transfer orbit at the same point. So you can see if the satellites want to be docking onto from initial orbit to the transfer orbit, it must have the certain change in velocity at the particular point. Otherwise, it will remain on the same orbit. So basically, when we want to change the orbit, we need to give a thrust. And that means kind of impulse and to move the things on. The impulse is to produce sudden change in the velocity given by this. These chapters will be focusing on how to calculate the impulse theta v. Okay, so we're going to learn most of the topic in this chapter is to learn how to calculate theta v, and here. Okay, so that is the whole highlight. So we can do the detailed calculations, and let me put certain calculations here. So say this is the point 1, this is point 2, and velocity point 2, let me call it V2, okay? And that is the symbols. So here we can determine how to determine the theta v, and let me call it this is theta v1 here. So here is the steps. The Hohmann transfer. Let me give you a definition. That is the transfer between two circular orbits. And actually, two coplanar. So basically, two initial and target orbits must be on the same plane. If they are out of plane, then we have a different technique we can talk about in the few other chapters here. And this one, that is this of determine the necessary V1 and theta V2. And you must know the transfer is taken for the half cycle of the transfer orbit, which means here we move from the south pole to the north pole of the corresponding orbit here. So how can we start with? So we can determine the V1 first. So V1 velocity at point 1 on the initial orbit, circular orbit. And this one we can determine is how can we determine circular orbits? Circular orbits, what is the speed on the circular orbits? I don't have a notes here. Anyone can help? Okay, we can start from here. E equal to, on one side is V squared over 2 minus mu over A. Say if we have a circular radius is R1, okay, and on the other side is mu divided by 2A, A is R1 here. Right? We can utilize these equations here. Okay, because here for R we have the R1 here. So therefore here we can determine the V will be equal to mu R1 square root multiplied by 2. Sorry, this one. Okay, so that is the velocity V1 here. Okay? Okay. Then we determine the V PR transfer, and let me give the name transfer at point 1. Okay, so this is the VTR. VTR1, so that is the velocity at point 1 on the transfer elliptic orbit. So again, we take up these equations. In general, velocity, energy equal to minus mu divided by 2A, right? And then also on the other side, equal to V squared divided by 2 minus mu over R. So for this one, at P1, at the point 1, we have R equal to R1. And also for 2A, for this elliptic orbit, the 2A, simply look at the graph here. That is R1 plus R2. Right, so we plug in those information, so therefore we can obtain, therefore V on the transfer orbit at point 1 can be equal to here is I directly calculate out the whole thing is R2, R1 plus R2. Okay? So therefore, in this way, you can determine the thrust. And the thrust basically is the difference of the two quantities. And right now, with those symbols, we don't know which one is larger and which one is smaller. And most of the time, I can tell you the energy the larger the the velocity you're going to have, the more fuel you're going to expend. Basically, here is the kind of the site information. This information is not provided by our textbook, but I somehow found it from somewhere. Delta M over M. Delta M is the fuel consumed, and that one is proportional to 1 minus exponent of certain constant. So C is the constant, certain constant, and delta M is the fuel consumed. And delta V is the disruption, which means the change in velocity. Okay, so that gives us a certain idea. So most of the time we concerned is the difference between the velocity. So really doesn't matter if we always taking up its absolute values. Okay, but sometimes I will ask you for the learning purpose, I will ask you when they change the velocity, they are going to accelerate or they're going to slow down. I might ask you these kind of questions. Okay, so that is the one here, and the same thing we can exercise at point 2. So we determine the V2 and V transfer at point 2. We can also determine this one. So at V2, again, V2 is on the larger, the final orbits have the same pattern here, so we can copy this pattern, mu divided by R2. And VTR2, the same thing, we can repeat the same calculations. So that one is this V squared over 2 minus, let me copy the equation again, equal to energy mu divided by QA minus mu R1 plus R2. So at R equal to R2, so we can plug in. So therefore, V at TR2 can be described by 2 mu R1 R2 R1 plus R2. Okay, so right now we have the two terms together, then we can also determine the delta V at point 2. And we can look at one example to see. So therefore, we can probably determine this one. Okay. And I will give you one example. But before doing that one, let me have one more the questions. How much time this satellite is going to take and from its initial to take for the transfer? Basically, that is a half of this transfer orbit period, right? So that means the time to spend time to take for transfer is half period of the elliptic transverse orbit. Okay, basically that one equal to how much? Equal to T transfer over 2, so that one equal to pi over mu. Okay, so that is this one. And we can take a look at one example to see what happens here. And let me save those and save those. Let me do this one here. So say example here, the R1 we have is 2 du, whatever the Earth distance, okay, and I allow me to drop this symbol. We know that is the Earth, so just use du. And R2 is 3 du. So with this information, we can calculate. So therefore, from here you can see we plug in. So V at V1, plug in all the information there. So that will be equal to mu divided by R1. So that is 0.707 DUTU. Okay, and then VTR1 on the transfer orbit. So that one equal to 2 mu. R2. So that one is 0.775 DUTU. Okay, so that means compared to this number, basically my drawing is correct. So basically here at this transfer point, you need to speed up and to dock onto the transfer orbit. Okay, so there's a 1, and then at point 2 we can calculate V2 equal to mu over R2. So that one. Let me ask you, before we come up with these numbers, right now the satellite is moving in the inner orbit smaller. That has a constant speed like this one. And the satellites on the outside, the outer larger orbit, which one has the faster speed? Without doing the calculations, do you have any common sense? Slower. Always slower. Okay. That reason on Earth, 1 year, basically one cycle around the sun is 1 Earth year, 375 days, right? How many days as a year on Mars? Right now, recently, NASA talked about a lot moving, immigrating to Mars. How many days? It's longer than Earth's year or shorter than Earth's year? It's longer than Earth's year, more than 1 year. And how about if Venus is okay to declare how much cycle of Venus about the sun? Only a few months. Because in there, the orbit, they're moving faster. Okay, so, and now we continue TR2. So that is 2 mu, and R1, R2, so that one equal to 0.516 DUT. Okay, the same thing here, let me draw that one. So this one, once to the central orbit, here the velocity is that big. So again, once these satellites reach a second transfer point, again, you need to speed up one more time. Okay, so therefore from here, velocity, therefore you can calculate delta V1, the first thrust, and if we only take out the magnitude, so 775 minus 707, so that one equal to 0.068 DUTU, and delta V2 equal to 0.577 minus 0.516. This is the amount, this is the numbers. If you the sum and up, that will be the information for engineer to determine, say, for these satellites before launch to this orbit. That is the information engineer need to determine, okay, how much fuel we need to load it up onto these satellites if we expect the satellites to do the transfer on his own. And that is a minimum number of the fuel we need to prepare. And that one is based upon the more complicated formula, but basically in concept is similar to this one. The thrust is in some certain way proportional to the fuel. Okay, so that big concept is this, and different situations. This one is a very simplified equations, but I believe they should have a certain manual or know-how, the book, and for you to estimate the fuel. Okay. So that's the reason why, because in most of the satellites, and say that is in the near Earth space, that means still have a little the atmosphere frictions there. So most of the time they have to adjust their orbit by putting certain thrust until their lifetime ends when they don't have any fuel anymore. So basically they, when they're moving, they encounter the little friction that gradually change, gradually slow down their, not slow down, gradually change their situations on the orbit, eventually either moving away or most of the time moving toward the surface of the Earth. So this one you can see this in this way. These chapters, most of these things will be on this one. And follow up is we will talk about the different transfer strategies. But again, the underlying principle is we simply determine the shape of the transfer orbits and the shape of the initial orbits and target orbits. We simply corresponding to the corresponding formula that is from our chapter 1. We simply do the calculations. And okay, so that is for this section.